So the wave system is essentially a couple oscillator system in a certain continuum limit. When the particle becomes so many, there are so many particles, and the spacing between the particles are so small, then the couple oscillator system will become wave. And wave system is almost everywhere in physics study. So that's why we spend a lot of time this semester on oscillator, so that you can understand more the details of the oscillator system, and then you can understand the wave system. And we talk a lot about wave system not only because it's everywhere in physics world, it is also because in quantum world, it's the easiest way to understand quantum system by studying wave. Because electron is not only a particle, it is also a wave. That's a huge discovery physicists found in the early 20th century. Okay, by studying wave, they know how to describe the quantum system of electron. Okay, so put that in your mind. That's the goal of our whole school year of study. And so today is a crucial point. We are going to move from oscillator to wave. Okay, so yeah, let's move on. But before we do that, I still want to spend some time giving you some animation picture about the oscillator system. Last week we talked about three-body oscillating system with three masses and connected by 4 springs. It's a couple oscillation system. And if you write down the equation of motion, you found that the equation of motion is here, and you found that it can be described, put into a form of matrix. And in this matrix notation, it's much easier to manipulate and calculate. Okay, so last week we put in this kind of gas solution, and then we found that, and this differential equation can be transformed into a eigenvalue problem for this matrix. The matrix is here, okay. And after solving the eigenvalue problem, we found 3 eigenvalues. We put it into omega 1, omega 2, and omega 3 in the order of their magnitude, okay. So the omega 2 is the one in the middle. After solving omega 2, we found the eigenvector to be -1, 0, 1. This eigenvector can only be determined up to a constant, so there is a constant C2 in the front of it. Okay, so you can, put in the other way, you can only determine the ratio between the 3 components. But remember, these 3 components, we call it A1, A2, and A3, are actually corresponding to particle 1, particle 2, particle 3. Therefore, it is sometimes useful to put this A1 and A2 and A3 on a diagram like this. Here, the A1 is -1, A2 is 0, and A3 is 1, corresponding to particle 1. Put it in the location of first particle, second particle, the third particle. Okay, so it's very diagrammatic. The point is, if you do it this way, then after solving the eigenvalue problem and put it back into the equation of motion, the solution is equal to A2 or exponential I square root 2 omega 0 t. Okay, so please observe that this exponential function is a number, and this A is a column vector. That means x1, x2, x3, the ratio between them is just equal to A1 to A2 to A3. In this case, it's -1, 0, 1. Okay, so that means this diagram will not only tell you the eigenvector, and the eigenvector will tell you how the 3 particles will oscillate in this pure mode. Okay, so let me give you some motion picture so that you can understand more about this solution. I found some motion picture on the web, and this is the second mode. We call it the second mode of oscillation. Okay, remember -1, 0, 1. So yeah, it's actually from a course by an open course from MIT. So this is you can see the professor waving in his lectures. So again, so this is what happened in this second mode of pure oscillation. Remember, if you look at it individually, oops, sorry. If you look at every particle individually, every particle is oscillating. Right? The middle one doesn't oscillate, but the other two are oscillating. Okay. Okay, so, and the ratio between them is -1, 0, 1. So that the left hand, the first particle is oscillating opposite to the third particle, while the second particle doesn't move. It reflects the fact that I told you x1 to x2 to x3 is equal to 1 minus 1, 0, 1. OK， 那个比例是一样的。好 ，x1 比上 x2 比上 x3 就等于 a1 比上 a2。所以呢，因为你的这个 x 呢，就是等于 a2 这个 eigenvector times 一个 number，therefore x1 to x2 to x3 is equal to a1 to a2 to a3. So if you know this eigenvector, you know how these three particles oscillate. Okay, you know the ratio between them, and it applies all the time. Anytime the ratio between them will be the same. -1, 0, 1. Okay, so it's a very easy way to understand the oscillating mode from the eigenvector. Okay, so that's the second mode. Let's move on to the first mode. First mode is, we call it the first one because the frequency is smaller. We order them in the order of magnitude. So this one, if you solve the eigenvector, is 1 square root 2, 1 times a undetermined constant. Therefore, you can put it in a diagram like this. So it is a1, a2 is square root of 2, and a3. So all of them move in the same direction, right? So now I'll give you a motion picture. This is what happened. Now all three particles look like they move together. Okay, but if you look more carefully, the middle one actually, the amplitude of the second one will be larger than the amplitude of the first one by a ratio of square root 2 over 1. Okay, so look at it again. You can, but again, look individually. If you look at every particle individually, separately, you will see that they are oscillating, just a simple harmonic motion. That's why we are calling this oscillation mode pure oscillation, because everybody is oscillating with the same frequency, but with the ratio 1 over square root 2 over 1. Finally, the third oscillator mode. Now the eigenvector is 1 minus square root 2, 1. So now you can expect the second particle will oscillate opposite to all the other, the other. Okay, so that's exactly what happened here. See, so this middle one actually move opposite to the other two. Okay, so it's 1 minus square root 2, 1. Okay, you can see it again. Okay. Now, I hope you are convinced. There are three eigenvector. There are three eigenvector corresponding to three eigenvalues The eigenvalue describes the frequency of the oscillation, and every eigenvalue will correspond to one pure oscillation mode. By pure oscillation mode, I mean in that mode, every particle is undergoing an oscillation. Okay, pure oscillation, just like a simple harmonic motion. Okay, and the number of the modes, in this case, there are 3 modes, actually corresponds to the number of particles. Okay, the correspondence is clear because it's a 3 by 3 matrix. If there are 3 particles, then the matrix will be a 3 by 3 matrix, and the 3 by 3 matrix will have 3 eigenvalues. Okay, because the characteristic equation has 3 solutions. Therefore, there are 3 modes, and 3 modes correspond 3 eigenvalues, and 3 eigenvalues correspond to 3 modes. Okay, there is a one-to-one correspondence between the number of particle and the number of eigenvalue, and then the number of pure modes. Okay, so now those are animation picture, but actually this professor in MIT actually demonstrate. If you go to there's a link in my PowerPoint to their site. Okay, there is an open course, so if you are interested in watching some of their lectures, you are free to do so. Just follow the connection in my PowerPoint. But I want to show you this little picture, little movie I extract from their lecture. Here he showed the 3 oscillation modes directly on experiment setup. Okay, so here this is the first mode. Okay, this is the first mode. You can see that there's 3 particles. Of course, they are connected by a spring. And then the professor set up the first mode. If you remember the first mode, the 3 move together. The second mode and the third mode are much easier to see. But this first mode, now this is the second mode and the third mode. Remember, in the second mode, the middle one doesn't move. The other 2 oscillate. Now, let's see the second mode. Okay, the middle one doesn't move at all, but the other 2 actually oscillates. Now, look carefully. Now the professor tried to adjust the frequency of the external force so that you can excite the third mode. Now he adjusts the frequency. If you look carefully, what he did is to adjust a line of oscillation so that this line can connect it to the oscillating system. So he is adjusting the frequency of external force so that it can adjust how this oscillation system, couple oscillation system, is excited. So now you have seen the second mode already. Now he adjusts the frequency so that the third mode is oscillated. The third mode, the middle one, oscillate opposite to the other 2. Okay, the first and the second move together. If you want to take a look at the third mode again, that's the third mode. The middle one move opposite to the other 2, while the first one and the third one oscillate together. Now, let's see the picture again. Here, a little bit earlier. Now the third mode. You can see that something is rotating here. Yeah. Okay. It adjusts the rotating the frequency. So see, the first one and third one oscillates, the middle one oscillate opposite to them. Okay, that's the third mode of the oscillation. You can, and the professor adjusts the frequency of this external force to determine which mode is excited. Okay, so the professor adjusts the external force frequency to be close to omega 2 or omega 3. Okay, remember I talked about resonance in the earlier lectures. If you adjust the external frequency of the external force close to the natural frequency of a simple harmonic motion, then that simple harmonic motion will be excited. Here, this system has two simple harmonic motions, actually three. Okay, omega 1, omega 2, and omega 3. If the external force is different from all three, then nothing will be excited. However, if you adjust, so that's why the professor is adjusting the external force frequency. If you adjust it close to omega 2, then the second mode will be excited through resonance. If you adjust it close to omega 3, then the resonance will excite the third mode. Okay, it's almost exactly like, if you remember, I've shown you this picture. A gas. Oh, sorry. Let me shut out the sun. Okay, but remember I showed you this picture already. Yeah. The oscillation here, the oscillation is the oscillation, the transfiguration of the glass. Okay, and the transfiguration of the glass has a natural frequency, just like our pure oscillation of coupled system. And then when the external microphone is turned on, the sound will oscillate, will exert the force on the glass. When the external force frequency is close to the natural frequency of the glass, that glass will be excited, so by resonance. So it is almost exactly the same mechanism by exciting the coupled system by the resonance. Okay. I hope these motion picture will help you understand these coupled system. And remember, what we have is our three coupled system. What we have are three pure oscillating mode. However, the usual situation will not be just mode 1, mode 2, and mode 3. Actually, they could be the sum of the three. Here, I showed you that if I put it in here, in this cartoon, here he adjusts the initial condition arbitrarily. Okay, for example, x10 is 1 meter, x20 is 0.9 meter, x3 is -3 meter. So it excited all three of the oscillating mode. Okay, so you can see that's what happened. It's not a pure oscillating mode. Here, the professor also lists x1 and x2 and x3. You can see this is the first mode, the second mode, and the third mode. So this oscillation is a linear combination of the all three pure oscillating mode. OK， 好，所以呢，这张图就秀给你看，如果你3个 mode 都一起 excited 的话，大概会发生什么样子的一个震动 ？OK， 好 ，it's hard to see how it's hard to see the relation between these very complicated oscillating modes with the three underlying oscillating mode. 你很难看得出来这个震动跟我们下面的这个模式彼此之间的关系。但是呢，的确，这个震动呢，就是刚刚讲的这个3个模式的 linear combination. You can see from the detailed formula above here. Okay, so the bottom line is that if we have a 3 oscillating mode solution, by taking the linear combination, you can form a general solution. Or in other words, a general solution can always be decomposed into a linear combination of 3 modes. 最终的一般解永远可以用这样子的 mode 的模式解 来把它那个加起来，好，叠加出来。In Chinese, it's called 叠加出来。Okay, so you can see that A1 with the cosine, A2 with the cosine, A3 with the cosine are sum up together, and Fi, F1, F2, and F3, G1 and G2 and G3, there are 6 unspecified constants. Then you can adjust these 3 constant so that it satisfies the initial condition. For example, if you give me x1 0, x2 0, and x3 0, I can write the condition. It is equal to AI, this is known, times Fi, and sum over it. Okay, expanded out, it looks like this. So it becomes a system of equation for F1, F2, and F3. Remember, these are the conditions the problem will give you. And F1, F2, and F3 are the number you want to solve. So 3 equations, 3 unknown, F1 and F2 and F3 will be solved. OK， 好，这3个常数呢，其实就可以解出来，好，就可以解出来。OK， 好，那这个呢是 F， 事实上 G 也可以啊。刚刚讲的这个结果是 F， 那 the other 3 constant G1, G2, and G3 will be determined by the other 3 initial condition x prime 0。OK， 啊，因为你一开始也要告诉我这些 particle 呢是起始速度是多少。OK， 所以呢 you will be telling me x1 prime 0, x2 prime 0, and x3 prime 0. With these 3 conditions, you can determine the other 3 unspecified constants, G1, G2, and G3. Okay? Therefore, with all the constant determined and the general solution satisfy both the initial condition and the differential equation. So we got everything solved. Okay, so that's the general procedure of what we will do. I take an analogy that the F1, F2, and F3, and G1, G2, and G3 are the initial recipe. Okay, just like you put everything together into a pot to cook it. Okay, and you have to tell me how many carrot I want to put in, how many tomato you want to put in. So that number are the initial F1, F2, and F3. That's the initial recipe. And if you and that will be determined by your initial condition. You have to tell me the recipe. Okay, and you put in together, and every ingredient will evolve on their own. Okay, so you can see that the ingredient, when the time passes, it will be multiplied by cosine omega it. If it is G, then it will be multiplied by sine omega I. Okay, so after a while, maybe after an hour, the soup is cooked. That's because every ingredient evolve according to their evolution and finally becomes a soup. Okay, okay, so that's an analogy how we solve the equation of motion here. Okay. Now we finally finished the 3-body problem. I'm not going to solve the n-body problem because it's too complicated. However, I can put out the formalism and tell you a few words, comments on how we are going to solve this problem if we have time. This is the n-body oscillating system or n-body couple oscillation system. Here we have n particle, 1, 2, 3, up to n, and they are coupled by a spring in the nearest neighboring particles. Okay, so it looks like this. Okay, and then every particle we give it a position. For example, the jth particle, the position will be xj. I should say displacement because the original position is here. Then xj is displacement away from the initial position. Okay, so you got x1, x2, x3 up to xn, and then the equation of motion will be something like this. because the jth particle, the displacement of the jth particle, the acceleration of it will be determined by the force and the two springs attached to it. Okay, this is the force exerted by the left-hand side, and this is the force exerted by the right-hand side spring. Okay, just like before. Okay, except that now we not only have three equations. In the case with three body, we have three equations, but here we have n equation. So it's a much more complicated system, even though it follows the same pattern. Okay, I can simplify this equation just like before into this form. And if you look into this form and impose a boundary condition that x0 and xn plus 1 is equal to 1. That means at this side, I put in another x0. However, this x0 doesn't move. Here, I put in another xn plus 1, but this n plus 1 does not move. Then this equation can be put into a matrix notation. Again, I can collect all the displacement of particle into a column vector like this, and the equation will be written as a x over t squared equal to minus a matrix, now an n by n matrix times x. Okay? Looks very complicated, but if you compare to the 3 by 3, you can see the pattern is exactly the same. All the diagonal element is 2, 2, 2, 2, 2, 2, 2, 2, and the off diagonal only one level up, one level down, minus 1, minus 1, minus 1, exactly the same as 3 body. Okay, so same pattern. It just extends the 3 body we have already solved into an n by n case. Okay, is that okay? So with this kind of notation, the equation of motion is quite simple. It is this very simple matrix equation. And again, if I assume the x to be a complex number, and then write the solution as a column vector A, just like before, times exponential I omega t, just like before, and then put it in, again, it becomes an eigenvalue problem. A times A is equal to minus omega squared times A, exactly the same as before. But now, again, the A is an n by n matrix, and this small a is a n column, consisting A1 dot 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 through AN. So this is the eigenvalue problem. Again, exactly the same pattern. However, in this case, don't you feel that it is a bit impractical to solve it by the requirements that the determinants vanish? Before this, I can say, oh, I want this determinant to be to finish, and I write down the condition. It's a equation, an algebraic equation of order 3. But in this case, if you do the same thing, it's an equation of nth order. So it's impractical to do it this way, right? However, up to this point, we can be sure this n by n symmetric, positive, definite n by n matrix, it is symmetric. Of course, you can be convinced by seeing this matrix itself, and then because it is a mechanical problem, so the potential is positive, as I say last time. So this matrix is also positive definite. So any symmetric positive definite n by n matrix will have n positive eigenvalues and n eigenvectors. Therefore, again, following the same principle, every eigenvalue, every eigenvector corresponds to one oscillating mode. We can expect this system to have n pure oscillating modes. That means in this n pure oscillating mode, they undergoing a pure simple harmonic motion. Okay, so this is for sure without solving the problem in detail. Okay, 我们不需要真的把它解出来，但是呢，你即使把它的问题呢写成这个样子，你都已经知道，你事实上呢，它的解会长像这样。OK， 好，所以呢，一个系统有 n 个一个 n particle n body 的系统呢，有 n 个 oscillating mode 是很确定的事情。 只有这件事情其实是最重要的，好，是最重要的。OK, of course, if you want to solve the problem, we can also try to solve the system. So it becomes a gray background because I'm not going to cover this part, but if you are interested, you can take a look. And in this case, I can still solve the eigenvalue problem, but this time not by the characteristic equation, not by vanishing determinant, but you have to write down the equation itself and try to solve it by an ansatz. Ansatz means a method by intuition, okay? In this case, the ansatz is that A1, A2, to AN is proportional to this form. Don't ask me why we understand that, but we just understand this is true, okay? So that's why it is called an ansatz. It's a German word meaning it's a method by intuition, okay? Actually, not by intuition, because we have already solved the system in the continuum limit. So we actually extrapolate or interpolate from the continuum limit to here. We know it must look like this, okay? But anyway, if you take this ansatz and then put it back into the equation, you can show this ansatz could solve the equation, and therefore you can write down the omega square, the relation between omega square and p. P is a certain constant here, okay? So we can ignore this part, but if you are interested, you can take a look. But here, you can see this picture are the original A1, A2, and A3 I show in the case of three-body problem. In the three-body problem, I draw this A1, A2, A3, Now, if there are n particles, then you will have a diagram of n points. So here, for the case of n equal to, I think it's 8. It's 8 particles. It's 8 particles. So there are A mode, 1, 2, 3, 4, 5, 6, 7, 8. And then, it's 4 particles. 1, 2, 3. So it's n equal to 4 system. So 1, 2, 3. Oh no, this is just the system we are talking about. That's the n equal to 3. Do I have a case with more particle? It's n equal to 3. And here is n equal to 4. Now I have 1, 2, 3, 4 particles. And this is A1, A2, A3, and A4 for the fourth modes, and this is for the third mode, for second mode, for the first mode. Okay, yeah, this corresponds to the diagram I wrote down. Okay, and you can see that I draw this picture from the AP I solved. Okay, the ansatz. If you put this back into here, then you got this picture. Some of you may observe that these diagram of A actually look like standing the 驻波 standing wave or standing wave picture. Yeah, if you think so, then it's exactly like that. Because remember, next I'm going to take this system into a continuum limit by asking n equal to infinity and the separation going to 0. Okay, therefore this system will become a real wave system. So therefore, it looked like a standing wave. It's not coincidence. Okay, it's really just what happened here. Okay. Now I'm going to skip this part. Okay, so now I'm going to go to the continuum limit or continuum limit. Okay, and you will expect that in this couple system with n particle, when I go to the continuum limit, you will look like this, because I'm taking the limit, the number of particles goes to infinity. However, I expect this system to be finite. Therefore, the spacing between the two particles will become 0. Okay, so I'm taking the limit of n equal to infinity and d equal to 0. Okay, that's the we call continuum limit here. Okay, continuum limit, how to do it? Any question before here? Before we start the continuum limit? Here again, the equation in detail and the equation in matrix notation, and the x now is a n particle column, x1, x2, to xn. However, when the number of particles becomes huge, then this column vector is no longer convenient because it becomes so huge, so large, right? So therefore, we need to adjust our notation. In this case, we will prefer a function instead of a column vector. Did you observe that? So this function will define by x, the position of the particle. For example, these particles x, this particle, the location, the original location is d times j for the jth particle. Then I will say phi dj is defined as xj. That is, the phi, the function at the position dj is equal to the displacement of the jth particle. Is that okay? Maybe I should put it in Chinese so they can understand. 我们现在呢，原来呢是一个 column vector， 但是呢，如果是一个 column vector 的话呢，你的这个就太多了，因为我们现在 n 要变成无限大，所以呢，我们期待把这样子的一个 information 变成是一个函数。这个函数呢，一开始的时候我定义呢，就是你的这个 phi 呢，在 dj 的这个位置 ，dj 呢就是 dj 个 particle 它一开始的这个位置，我定义 dj 的这个位置，它的这个值。就是这个这一个 particle 它的 displacement. Is that okay with everybody? So it is defined as xj. Remember, xj is the location of the particle, is the position of the particle away from its original position. Original position is dj for the jth particle. So xj is the displacement from it. So you can say that for the jth particle, maybe I should put this on my transparency. For the jth particle, the position will be dj, that's the original equivalent position, plus xj. That's the position. Okay, so I'm transforming this xj into a function phi at the j's place, but I design so that it is a function of the original position. Okay, but I know because this xj connected to this j, therefore the two numbers are connected with each other. But anyway, in mathematical terms, I just define phi dj is equal to xj. The displacement is not the original place, 它是位移。dj 是它的原来的平衡位置，位移呢是 xj， 所以我才会说 dj 加上位移就是那个时候的这个粒子它的这个位置。Okay, so you have to separate the original place, position, and the displacement. Or if you put the two together, it is the position of the particle at the moment. Okay, ma? So, in this way, I transform a column vector into a function. That's the key message. I transform a column vector into a function. The reason is simple. Because the column vector, when n equal to infinity, it is difficult to manipulate. It's difficult to calculate. But the function is everyday life, right? So therefore, I replace the function I replace the column vector by a function. However, up to this point, this function is only defined for discrete position, dj, right? However, when I take the continuum limit n equal to infinity, and d equal to 0. This dj, originally it is discrete, will be approaching a continuous number or a continuous variable. Now I will call this x. Okay, so originally it's a function on discrete position. Now it becomes a function of continuous variable. We call it phi x. This phi x now is a real function of a continuous variable x. However, it also depends on time because it will change with time. Therefore, it is a function of x and time. It's a two-variable function. Ladies and gentlemen, we call it wave function. That's the central object we are going to study in the wave system. But you can see the origin of this thing, of this most important object in wave system, is actually the column vector, a collection of the position of a couple's oscillation system. 所以呢，这个呢函数 phi 最早的时候呢，事实上呢是一个 column vector。我们把它变成是一个函数的时候，事实上只有在这个粒子的原来的那些位置 dj 它才有值 ，OK 它才有值。对啊，当然啦，因为只有你的定义里头 phi dj equal to xj， 所以呢，你的这一个函数只有在 dj 的地方才有值啊。dj 是一个的分离的这个数嘛，不是如此吗 ？OK， 那现在我如果取了一个那个 continuum limit 了以后，让 n 趋近无限大，让 d 趋近于零，那么这个 dj 现在就变成是一个连续的函数。So this is very important. When we take the continuum limit, dj, the discrete location, becomes a continuous variable. So this phi j now becomes a function of x, but it is also a function of time. Therefore, it is a two-variable function. We call it the wave function. 那这个波函数呢，是整个讨论波的现象的时候最重要的一个对象。最重要的一个对象。等一 From here on, you'll hear about wave function almost every time we have class. Okay, because we are going to talk about it in the classical wave equation. We are going to talk about it in the Schrodinger equation. So wave function. But remember, the origin is here. 它的原型 the original form is just a column vector. You collect the position of these particles into a column vector. 你只有当你做了一个 continuous limit 了以后，这样子的 column vector will becomes a function. 好 ，OK, so on this page, I also list a comparison between discrete couple system and continuum system. Okay, so dj corresponding to x after we take a continuous limit, and xj as a function of t now will correspond to phi dj as a function of t. Okay, so it becomes, and after taking a continuous limit, dj becomes a continuous variable x. So xjt will correspond to phi xt. Okay. Is this comparison table helpful for you? 所以呢 we move from oscillator to wave after this continuum limit. So next step, the most important step, is to go from the original equation of motion of couple system into a wave function. This is the most important derivation today. Okay, it's very complicated. Maybe some of you will find it very abstract, so will go slow. But it's the most important step today. Okay, so now I'm going to transform the original equation of motion. Again, the original equation of motion is a matrix equation. Okay, but I prefer to put it in this detailed form of components of matrix. Okay, so I'm going to take, I'm going to find an equation for the wave function from this equation motion of a couple system. But this transformation is actually very, very simple. All we need to do is to plug in the corresponding quantities. By corresponding quantities, I mean xj correspond to phi dj. So this x plus 1, so this xj will correspond to phi dj. This xj plus 1 will correspond to phi dj plus d. Is that okay with everybody? Actually, that's the only significant step in this derivation. Even though the derivation is complicated, abstract, but this is the only essential step. I replace the quantity in the original couple system with a notation that is good for wave. So xj is replaced by phi dj, x plus 1 is replaced by phi dj plus d. And then again, here the same, this is replaced by this is replaced by this. And xj, of course, it is phi dj. And then I take a second derivative of t with respect to t. It's okay, because this depends on time. So that's the position of the jth particle. In the new notation, it's the function at dj, and it's, of course, a function of time. So I can take a second derivative of it. I hope this step is okay with everybody. If you can understand this step, then everything is done, actually. You just need to simplify the notation. First step, here I have a phi minus phi. So I call it, that's the difference of the displacement at the jth particle. That's the j plus 1 phi. If you take a look at this picture, this is this, minus this is this. So I call it the difference of displacement. Now I divide the difference of displacement. I replace this difference of displacement by this notation delta phi, and then I divide it by d. When you divide it by d, you need to multiply by d so that the two will compensate each other. So this term will become this. This term will become this. Very similar. Except that this term is evaluated at dj, and this term is evaluated at dj minus d. So dj minus d. Okay? However, when you put it in this notation, delta phi over delta is actually a derivative when d goes to 0. Okay, we take the first step towards the continuum. The first step, delta phi over d, is actually d phi over dx, right? Because this d is the separation of the variable, or difference of the variable. So here I have a difference of function divided by the difference of the variable. So it is d phi over dx. Again, if you evaluate it at dj. Minus the second term is exactly the same derivative, however now evaluated at dj minus d. Oh, okay, so now I have the difference of derivative. Originally I have a difference of function or difference of displacement. Now I have a difference of a derivative. So I can do it again. So the difference of a derivative, I will write it as delta d phi dx. And divided by d and times the d to compensate it. So it becomes kd squared delta d phi over dx over d. Written this way, now it's clear again, this is the derivative of the derivative. So that's the second derivative, ladies and gentlemen. Therefore, we can simplify it into k times d squared phi over dx squared, evaluated at dj. After this transformation, the key effects is that we go from a notation for discrete system into notation for a continuum system. Even though it's still evaluated at dj, however, the notation could be upgraded right away into a continuum system. 再次 in Chinese， 原来的 notation 是一个分离离散的系统， 一颗一颗的 dj。但是呢，经过像这样子的一个 transform 了以后，你就变成了 phi 对 x 的2次微分。这个符号虽然还是在一个 discrete system， 但是它立刻就可以用到 continuum limit 里头。对于一个连续的系统，它也是对的。OK， 来，谢谢。
可以讲一次，就是从 define， 从 delta phi 除以 d， 然后怎么变成 define dt。
这一步到这一步是？
对 ，define dx。
OK，you have 你要his question is from this step to this step, right? So you are asking why delta phi over d is equal to d phi dx.
Yes.
Yeah, remember phi is a function of x,
Yes.
right? So delta phi is the difference of function. And d is the difference of x. So you better, if I write it this way, delta phi over delta x, then you'll be satisfied that is d phi dx, right?
Yes.
And delta x 就是 d 啊。Okay, you have to recognize the delta x, that the d is delta x. That's the difference. If you take a look at this picture, it's the difference between the two particles. So it's delta x. Okay, and above delta phi is the difference of the function at two particles. Okay, so that's delta phi. So delta phi, again, delta phi is the difference of function corresponding to this difference of variables. And according to your calculus class, the difference of function divided by difference of variable should be defined as the derivative. Ask question if you have any doubts. That's a key step. But I only use what you learned from your calculus class. Again, delta phi over delta x is equal to d phi dx. You only need to recognize here delta x is the difference between adjacent particles. So it's d. And delta phi is the difference between function at adjacent particles. Let me put it in Chinese. Delta phi 是邻近的2个粒子之间的 phi 差。d 呢，就是邻近的2个粒子的 x 差嘛，所以我说它是 delta x。当然因为 delta x 就是2个之间的位置差，那就是 d 啊。所以你要记得这个 d。Maybe next time I add one more line to write this d as delta x. Maybe put a line here and write this d as delta x. Then you will see delta phi, delta x. And if it's delta phi, delta x, I think everyone will be convinced delta phi, delta x, taking the limit, delta x go to 0. Remember, we are going to continuum limit, so d will go to 0. So that corresponds to delta x go to 0. So I hope this detailed explanation will convince you that I can write it as d phi dx. Good. Okay, so I hope everybody more or less are happy with this step. Okay, so if this could be written as d phi dx, then the next step is exactly the same thing. Except that the next step, I am taking the derivative of the derivative. So it's a double derivative. So it's d squared phi over dx squared. Done. So it's a second derivative of the phi. I'm done with the derivation actually. Because the right hand side has been simplified, even though it's complicated in the beginning. However, after some consideration or unexpectedly, it is very, very simple in continuum limit. It is unexpected. 在原来的 discrete 的情况之下，它的右手边非常复杂，但是没想到你经过了一个 continuum limit 了以后，在连续的这个情况之下，右手边竟然非常的简单，就是 phi 的2次微分。That is unexpected actually. That's the benefit of going to continuum limit. by replacing by replacing the column vector with a function. Then the right-hand side becomes so simple. And the left-hand side is simple originally. It is just a phi over dt squared. So I simplified the original equation into phi over dt squared equal to a certain constant phi over x, second derivative. Okay, so you need to plug the step. You need to finish the constant. So it's k d squared and the m. And m taken to the right-hand side becomes k d squared over m. Okay, ladies and gentlemen, wave function. The second derivative of the wave function is equal to the second derivative with respect to x of the wave function. Okay, of course, I'm writing in the wrong notation. I still use d. No, d is the ordinary differentiation, right? The ordinary derivative. However, here I now have two variables, t and x. So this notation is wrong. It's correct originally. However, at this point, I have to remind you that this dt squared is differentiated when x is fixed. Of course, because when I take this derivative, I fix the location at dj. Right? So x does not change when I take this second derivative. Oh, you remember from your calculus. Your classmate just told me last week you just finished partial differentiation in your calculus, right? Okay, so that's great. It's a good timing. Then I can directly tell you this second derivative of dt is actually written as partial differentiation with respect to t. In Chinese, 这个 dt 你在做这个微分的时候，事实上是你的 x 没有变嘛，你就叫它叫做 dj 嘛。你是 dj 的那个家伙，那个 dj 的 particle， 它的位置的 second derivative。啊，你当然是在同一个地方去算这个 second derivative of t 啊。所以呢 ，that means if you examine carefully， 如果你仔细的看的话，你的 x 是不变的。当你做这个微分的时候，各位同学，当你的 x 不变的时候，做一个时间的微分，你们刚刚才学会的 calculus， 这个呢就是 partial differentiation with t。So this is a wrong notation. It should be written as phi partial square phi partial t squared. Same thing on the right-hand side. When I do this step from here to here to here to here, I fix the time. I didn't write time in the expression so that it is not too confused. However, I can put a time here, put a time here, put a time here, put a time here, put a time here. The time is fixed at a certain time. Okay, so that means when I do this differentiation, I fix time. When I fix time and doing the differentiation with the x, which should be written as a partial differentiation. Okay, so ladies and gentlemen, now finally the correct form of wave equation. Partial square phi partial t squared equal to this constant times partial square phi partial x squared. Okay, and this function this constant kd squared over m, usually we prefer to write it in terms of kd over m over d. Look carefully, m over d is just the mass per unit length. And this k times d will be defined as tau, which corresponds to the elasticity of the particle. So this square root of complicated expression, I will call it as v, the wave speed. Okay, the wave speed. It corresponds to what you learn from in your general physics, it is square root of tau over mu. 在普物的时候，你们导这个波方程式的时候，如果是一条弦的话，这个常数呢就会叫做 tau over mu。所以呢，这个 mu 就对应到这里的 m over d， 这个 tau 就对应到这里的 k 乘上 d。Anyway, I can always call this guy a constant v. then it becomes this equation of motion. Wave function, ladies and gentlemen. Therefore, in this comparison table, I can add one more entry. On the discrete side, we have the matrix form of equation of motion. It corresponds after the taking the continuous millimeter corresponds to the wave equation. Okay, so from here, we finally move from oscillator to wave. And this originally equation of motion is the ordinary differential equation, or I should put it more precisely, it is a system of ordinary differential equation. Now, it becomes a partial differential equation. Okay, so partial differential equation, the original form is actually a system of ordinary differential equation. I hope it helps you to move from a simpler form of mathematics into a more complicated form of mathematics. So it opened the page to partial differential equation. That's the main focus of the next semester of our study, wave equation. Any question? Oh, I have one picture so that I should have put in more picture today, but this morning I don't have much time, but here. Yeah, that's the wave. Okay, that's what I call the wave system. And of course, there are also another wave system, which is the horizontal 那个纵波，一个是纵波，一个是横波啊 longitudinal wave and transverse wave. Okay, that's longitudinal wave. This is transverse wave. Okay, but I'm going to show you that they correspond to the same equation of motion. So that's the longitudinal wave. I have derived this equation from a couple system. And next, before we have a 10 minutes break, let's derive the equation for a transverse wave. I think Professor Liu has already covered this in your general physics, so I'll go very, very fast. But just to remind you that the two derivations are very, very similar. Transverse wave of a string, transverse wave of the string. So string are consisted of very small segment of string. 一条弦，你可以把它切成一小段一小段。这一段我会讲得非常的快，因为呢，这个刘老师应该已经讲过了，只是再提醒大家一次。横波它一样可以用非常非常类似的方法，跟我们刚刚的纵波推导出一模一样的这个方程式来。OK， 好 ，So let's look at this small segment of string. So we are deriving the transverse wave equation for a string. Okay, so consider this small segment of string, and I consider on the right hand side there is a tension, on the left hand side there is a tension. We call tau in this notation, tau. Okay, so this tau, when in approximation, this tension will be equal to this. This tension will be equal to, this tension will be equal to this. This tension will be equal to this. So in this picture, I call this transverse tension as tau. Actually, it should be this one. However, because the string does not oscillate very violently, okay, the movement is very, very small. Therefore, this theta is very, very small. So in the limit, the theta is small, then the force here, the tension, will be equal to the force here. OK， 所以原来的这个 tension 应该指的是沿着这个绳子的方向，可是因为你的这个角度如果非常的小的话，这一段跟这一段的力应该会差不了太多。OK， that's the approximation we have to make to get the wave equation. Okay, so let's assume that the horizontal force are the same. So this tau here is tau here. But what we are concerned is the transverse force, because the particle, this line, will move in the transverse notation. Will move in the horizontal direction. 我们关心的是这条弦呢，在这个垂直的方向是怎么动的嘛 ？OK， so we care about this force, the tension force, the component along the horizontal the direction. Okay, so but it is very easy to calculate. For this one, on the right hand side, it is tau times tangent theta. Theta evaluated at x plus delta x at this point. Okay, on the left hand side, it is tau times tangent theta x. Theta x evaluated at the left hand side. The key is to observe that they are actually the same notation. However, one evaluated on the right hand side and one evaluated on the left hand side. And this function tangent theta, we can easily calculate it as partial y, partial x. Okay, because for obvious reason, partial y, partial x is the 斜率, the slope of this line. Therefore, tangent theta is equal to partial y over partial x. Therefore, f2 minus f1 in the horizontal direction will be tangent theta x plus delta x minus tangent theta x. Tangent theta is partial y partial x. So this expression could be written as tau times partial y partial x evaluated at x plus delta x minus partial y partial x evaluated at x. So that's the difference between partial y partial x at two sides. Okay, so-called the partial difference of function. And therefore, it could be approximated by the change of partial y partial x times the change of variable. Okay, so this difference could be written as partial y partial x, again taking a partial derivative with respect to x times the difference of delta x. Okay, therefore the force is equal to partial y partial x squared times delta x times tau. That's the force exerted on this small segment. Then according to Newton's law, it must be equal to the mass of this segment times the acceleration. The acceleration will be y, taking the second derivative of time. Okay, therefore, and the mass of this segment will be mu times delta x. Mu is the mass for unit length. So mass for unit length times the length of the segment, that's the mass of this segment. Okay, well done. Then left hand side is the force, right hand side is mass times acceleration. Cancel out delta x, and taking the tau to the right hand side, we arrived at the same wave equation as we derived from oscillation system. Okay, so this is, because this is too complicated, I simplify it in this page so that again, force, mass, and acceleration. And the force could be derived from the difference of the slope. The slope is the first partial differentiation with respect to x. Therefore, the difference between the slope will be partial y partial x, again taking the derivative. So that's the second derivative. That's why there's a second derivative of x. Right hand side, acceleration, so there's a second derivative of time. Therefore, we got the wave equation. Okay, so wave equation, we have derived it twice. One for coupled system, for the continuum limit of the coupled system, actually for longitudinal wave. Here, I could do it quickly. We derive it for the transverse wave of a string. Okay, next week, I'm going to derive it the third time by Maxwell equation. I will show you that by Maxwell equation in the vacuum, it will satisfy exactly the same wave equation. 下礼拜我们已经把这个波方程式呢推导出2次了 ，OK， 一次呢是纵波，我们从 coupled oscillation 出发 ，taking continuous limit 得到了它的这个纵波的这个波方程式。这里呢我们是横波 从一条弦的这个波动F 等于运动方程式出发，我们也一样得到了一模一样的这个方程式。OK， 下礼拜我们再推导出第3次。OK， so it's interesting, it's exciting because every phenomenon we call wave. Whether it's a sound wave, it's an earth wave, it's a surface wave, or string wave, electromagnetic wave, even the Schrodinger wave, electron wave. They are all described almost exactly the same wave equation. So that's the essence of mathematical physics. You do it once, you solve the equation once, and you can use it for the rest of your life. 你只要导一次，一辈子都可以用。Okay, so that's why we concentrate on this wave equation almost for the rest of our semester. OK， 好，现在我们休息10分钟。好，等一下呢，我们就要开始来介绍。到这里有没有问题 ？Wave equation。好，所以呢，接下来大概在50分钟的40分钟的时间，我们要介绍马克斯韦尔方程式。好，下礼拜我们就要用马克斯韦尔方程式呢来推导出这个电磁波的波方程式。好，那我们休息10分钟。好。